Okay, I think we should get going. So welcome to today's Department of Earth Science and Engineering seminar. It's my great pleasure to introduce today's speaker, Maurice Dusseault, who's Professor in Geological Engineering at the Department of Earth and Environmental Sciences at the University of Waterloo in Canada. So it's a very early start for Maurice to give the talk today, and we're very grateful for him to getting out of bed to give the talk. So Maurice asked me not to spend too long on his very long and distinguished CV. I will just say that he is a world expert, an acknowledged world expert in geomechanics that includes drilling, hydraulic fracturing, and reservoir geomechanics. And that prompts me to remind everyone, please, to stay muted throughout Maurice's talk today. And if you have any questions for Maurice, please type them into the chat, and we will pass those questions on to Maurice at the end of his talk. But without any further ado, Maurice, I'd like to hand over to you, please.
All right, thanks very much, Matt, and thanks for inviting me. Moving right along here, let's see if my screen all works. There. So this is news from about a week ago. The United Kingdom wants its first 2 carbon dioxide projects up and running by mid-decade. And yesterday, I convened a workshop for Southern Ontario heavy industry here on carbon dioxide sequestration within our little sedimentary basin. So the subsurface is becoming of much greater interest for society for many reasons, and I'll introduce you to some somewhat different ideas on potentially using the subsurface to aid the energy transition. And this is one of the reasons. It's the externalities associated with the combustion of fossil fuel. In this case, the pollution is due to PM 2.5 and some kind of gassy, a soup of gases that react with ultraviolet to create this midday pollution smog. This is in Sao Paulo, and these things are quite common in large urban environments. So the energy transition implies decarbonization. In other words, replacing fossil fuels. In other words, not putting new carbon into the atmosphere. And that implies a lot of things, amongst them different transportation fuels, displacement of coal and oil with other things. I list wind and solar and geothermal here. Improvements in efficiency and storage. Certainly here in Canada, with cheap energy, we are energy pigs, and we have a long way to go to make our buildings and our built infrastructure more efficient, maybe even retrofitting our infrastructure to consume less energy in many ways. So I'm going to talk about the subsurface as an aid to the energy transition. And once again, I remind you that it's partially a quality of life issue in many parts of the world. Not so much here in Canada. We're in fairly good shape, but along the east coast of China and India and Mexico City here, these are issues. So the World Health Organization is very clear about this. They have said that air pollution kills an estimated 7 million people because of the pollutants. And of course, naturally, low and middle income countries suffered the worst. Romania, now part of the European Union, has a long history of extreme pollution for their 2-3 major cities, and they're working hard right now to try to abate that level of pollution in their cities. Okay, so the subsurface and energy transition, I'll try to outline some somewhat different ideas, but in general, we can use the subsurface for natural gas storage. And I remind you that natural gas is a very clean fuel. And many of us, myself included, believe that natural gas could serve as a transition fuel, and using natural gas for one generation to build the infrastructure as we move towards a hydrogen economy. Because if we just say no natural gas, when it comes to putting into place a hydrogen economy, then we're just going to have to spend a few trillion extra dollars at that time. carbon sequestration, secure liquid and solid waste injection, energy storage with pumped hydrocompressed air, storing heat, and also in certain climates, storing cold. And yes, I know in Canada it's a bit bizarre, but I'm actually looking at a technology to store cold in the subsurface for warm climates, evidently. Geothermal heat and power, and other issues. So when we think of the subsurface and energy, we kind of normally think of, something like this. This is an array of natural gas wells in Texas. Yeah, that's big steel. But we can also use big steel for sequestration and for other purposes to access the subsurface. In general, we're using well bores, not exclusively, but in general. So I'm going to talk about narrower topics, things that I've been involved in, and one of them is subsurface biosolids injection. And the nice thing about that is that it is a safe and economical treatment method compared to the complex civil engineering treatment facilities that you use in Great Britain and in other places that are economically well developed. The nice thing about putting biosolids in is that you sequester the carbon, the excess carbon, and it also generates methane by the methanogenic archaebacteria that are in the ground everywhere that will degrade the carbohydrates into methane and other gases, and leaving behind the carbon as solid material. We're all geoscientists. We know that this is simply the process to make coal. So we can sequester huge amounts of carbon in this manner. We'll look at enhanced geothermal systems and sedimentary heat. We won't look at high-grade geothermal at all. And I'll finish up by looking at energy storage methods, something that I spent a lot of time on recently, compressed air storage in particular, but also looking at heat storage. Biosolids injection. Essentially, we're looking at the injection of a slurry of wastewater and biosolids. And of course, you and I and everybody produce on average about a half kilogram of dry biosolids every day, which is dominantly organic molecules that have to be treated. So this is the world's first injection facility for biosolids. I was involved in this. I have a patent on this, which expires next year, by the way. And essentially, we are going to slurry some biosolids with wastewater, inject it, anaerobic decomposition takes place. Methane is generated at about 12 to 15% of the dry mass. There's a wide range depending upon the composition of the biosolids. Carbon dioxide, which is extremely soluble in water, is another byproduct, and the carbon dioxide will enter into solution in the formation water. And that leaves carbon to be permanently sequestered, and a lot of it. At depth, the environmental risks are extremely small. You're not going to have the solid carbon escaping ever. And we have some energy recycling. The methane can be recovered. So calculating it out per year, it's more than 600 kilograms per person, carbon dioxide equivalent. Multiply that by large population centers, and you can see that this is not small and it's continual. In other words, we're always sequestering solid carbon permanently. Conceptually, we have a treatment facility at the surface that accepts the biosolids and slurries it. Injection under hydraulic fracturing conditions, that's necessary. We can't put solid material into the earth without hydraulic fracturing, but we know how to do that. And then, of course, at a later date, methane production. We want to be in a place where we have low permeability strata above us for security, good lateral permeability for the leak off of pressures. In other words, high permeability zones above you are good. That causes a leak off, which gives you more security. and a secure wellbore with an injection, tubing, instrumentation, etc. In the tire project in Los Angeles, the digested sludge is injected into an old oil field at a depth of about 5,000 feet, but a saline aquifer will be just fine. All dangerous agents and human biosolids have a very high concentration of metals. And of course, there's chemicals that you flush down the sink, and there's viruses, and there's other active agents in this biosolids, and these are permanently sequestered safely. In other words, we get rid of them, and the subsurface will treat them over time. Organic materials will be decomposed by the bacteria, chemicals will be absorbed by the clay minerals, metals will be sequestered by chemical processes as well. And of course, the carbon sequestration is in solid form, which means it's fully secure, plus methane. And of course, you can co-inject other waste. And I just show you an example of tank bottom sludges from the oil industry. This is a shot in Saskatchewan, and you can see this sludge is about 30% oil, 20% silica type minerals, and 50% water, and it's extremely expensive to treat. Well, it can be disposed of at depth. To give you an idea of an oil field injection operation, this is one of the larger ones in the world in Indonesia, currently inactive, and sludge is collected from all kinds of facilities, brought to this central facility, slurried and injected. In the UK, you have to look at the geology. You have to look at and get the right geology. And just looking at the geology of the UK, the geology in the estuary of the Thames and in the Wash, maybe shallow offshore, seems to be very good, very ductile sediments and appropriate saline aquifers at a moderate depth, 500 to 1,500 meters. Ideal situations for biosolids injection. There are geomechanics issues to manage. The injection is under conditions of hydraulic parting. Pore pressures in the target formations must dissipate rapidly to avoid regional pressurization. And we have some limits perhaps for a single well, maybe on the order of 50,000, 100,000, 200,000 cubic meters on a solids basis. That's maybe the limit for a single vertical well. And there will be stress changes. And that means that the initial in situ stresses are going to be altered quite massively. We will be increasing the lateral stresses a great deal. And that's going to change our fracturing behavior. And we want to understand these changes in order to give us a better idea of containment. We want to understand the potential for causing the shearing of bedding planes, especially smectitic clay, weaker bedding planes, which can cause wellbore damage and impair our process. We want to look at the ductility of the target formation and the overlying beds to make sure that we are sequestering these materials. But I do point out that after about 18 months to 5 years in situ, the toxic agents have been either digested by the bacteria or have been absorbed onto clay minerals and are no longer mobile. The next issue that I've been working on is low-grade geothermal energy, power and heat from the earth, and many of us have been working on that. And I just want to remind you that Canada is cold. So this is a map compiled by Steve Grasby of the Geological Survey of Canada from limited data that is available. But that great big white central part, that's the Canadian Shield, it has a low geothermal gradient. It is one of the poorest places in the world to try to go down and mine heat. On the other hand, we have just a few areas in British Columbia on the far left and maybe into the Yukon that could give us high grade steam, dry steam or wet steam, but we haven't found any reservoirs yet. And then In Alberta and Saskatchewan and on up into the Northwest Territories, we see a sedimentary basin, the Western Canada Sedimentary Basin, which has warm fluids at depth. And by warm, I mean for good saline aquifers, you know, you're going to be in the 110 to maybe 120 degrees Celsius range. So Canada is not only cold at the surface, it's also cold in the subsurface. And to show you that it's cold in the surface, let's look at this capital city of Nunavut, Iqaluit, just to give you an idea of the climatic conditions. Yes, that's right. A hot day in July is 8 degrees Celsius. Iqaluit makes London look definitely tropical. So that means that we have massive heat requirements in the north and no requirements for air conditioning or cooling. That means that we have some constraints on the use of ground source heat pumps as a means of heating and cooling, because we don't need cooling. So if we start looking at some depths, we're going to try to find porosity and permeability if we want to extract fluids. In the Canadian Shield, that is not a possibility. If you do have permeability and porosity, then you can bring the warm liquids to the surface. The upper part of the cartoon on the right are the basic elements of a power generating system. The most common, of course, is an organic Rankine cycle engine. And the first commercial project, the DEEP project in Saskatchewan, right on the American border, is on its way to producing commercial power in January. All of the holes have been drilled, and the surface facilities are being built and finalized as we speak. They have already received permission to increase their project from 5 megawatts to 20 megawatts right away, and they are looking at the prospects for other power generation plants in the subsurface. Now you notice I'm saying power, electrical energy. Why electrical energy and why not heat? Well, heat cannot be shipped 500 kilometers. So electrical energy is very, very dispatchable, very shippable, very good to send out to remote areas that need it, whereas heat has to be used locally. Even though we want to mine the heat and use it for domiciles in Canada, that's a local issue. This project is 3.2 kilometers deep, about 115 degrees Celsius. And to give you an idea of the requirements, to generate 5 megawatts continuous power requires about 200 liters per second of 115 degrees Celsius brine. Furthermore, the brine that comes out is not at ambient, it's at 65 degrees Celsius. So there's still a lot of sensible heat that could be extracted from that fluid. But you saw the picture, that's out there in the prairies. There is no use for the heat at the present time. That's unfortunate. That means that the warm water is just going to be recirculated and there will be attendant losses. Now, if we don't have permeability and porosity, the idea for an enhanced geothermal system is to identify a zone of hot rocks or hot fluids or warm rocks, access that zone with well bores, bring the heat up to a processing plant, and use the power and heat as best you can. In general, we believe that these systems are not sufficiently permeable at the beginning and will have to be hydraulically stimulated to generate the interwell connectivity required to successfully mine the heat at a commercial level. Probably at least 100 degrees Celsius rock is going to be needed, preferably more, of course, but more means deeper, deeper means drilling expenses. So we need a method to get the heat from the rock, to bring it to the surface, and to use the thermal energy effectively. And I keep on emphasizing heat. In Canada, we have need for the heat. The two big issues environmentally are fluids management and the potential for microseismic emissions, or shall we say small earthquakes, as a result of the thermally induced strains in the rock mass, combined with the higher pore pressures that might be used to drive the injection process. So once again, to develop it, we have to create a permeable environment. We have to circulate the fluids through this hydraulically stimulated zone and bring them to the surface. So hydraulic stimulation, a primary loop. Remember that as we put in fluids into the rock mass, the fluids come back up mineralized, unless we're using carbon dioxide, something that many people are looking at. That means that we have two different isolated loops, and we have to have a heat exchanger to scavenge the heat from the primary loop to use in the organic Rankine cycle engine. However, don't get fixed on an organic Rankine engine. We and others are developing new ideas, such as combining compressed air energy storage with geothermal heat for power, even cooling. If you give me compressed air and low-grade geothermal heat, I can generate power, but I can also give you the output air at about 2 or 3 degrees Celsius, and that would be wonderful for places like Mumbai or Nairobi to provide cool in a hot climate. Another way that is being examined is heat conduction. So this is the EVER concept. The website is listed there, and it's conduction in the rock mass, not convective exploitation by injecting a fluid into the rock mass. The fluid is circulated through sealed wellbores, either cased or sealed in another way. And full-scale field trials are ongoing in central Alberta. And remember that conduction is slow. You're going to need a lot of wells, preferably a high temperature. You're going to need efficient power engines. And again, I want to remind you that the organic Rankine cycle is not particularly efficient. Even with the delta T that you can use, it still will only extract about 15, maybe a little bit more % of that energy as electrical energy. There's a huge amount of waste heat in the organic Rankine cycle system. But again, my final point, in cold climates, that heat has significant value. So let's just briefly remind you about the world's largest project in this regard, the mining of heat. In a town just west of Helsinki, a town called Espoo, the world's deepest, I'm going to call it low-grade geothermal heat mining activity is ongoing, is being developed. And there you see the drill rig, the world's largest geothermal drill rig from Strata Energy, company run by some United Kingdom entrepreneurs out of Jersey. And they have drilled a 7-kilometer deep hole. But we all know that drilling costs increase exponentially while the heat in the rock increases linearly. So that means there are very severe limits to the commercialization of EGS with depth. This idea of, hey, let's drill down 15 kilometers. I'd like to remind you that the deepest hole we've ever drilled in the world is somewhat over 12 kilometers, and that took many years to drill in the Kola Peninsula in Russia. So the Finland project is looking for heat exclusively. They want to heat a subdivision exclusively, and they claim that they will be able to mine about 35 megawatts of heat at the maximum output of the system. Of course, in the summer, you're not going to be using this very much, but in the winter, in the coldest months, you need that heat. So 35 megawatts is their claim. Remember that if you do use geothermal for heat only, It's much more efficient than trying to generate power, but it's a local technology. No transmission is reasonably viable. I mentioned the binary cycle. I just want to emphasize that we stimulate a region, we work through a primary loop, and there's a lot of people that are looking at different technologies for this binary cycle power plant to try to extract more power from it. But we are, of course, limited by the laws of thermodynamics. And Monsieur Carnot, who was a professor at École Polytechnique, I believe, back about 200 years ago, he kind of laid down the big lines for the efficiency. Most of you know about the Carnot cycle, which tells us how much power we can get out. Okay, look at bullet number 1, Jean-Paul. This is where you are. We've got to learn how to drill these deep boreholes much, much more cheaply, because they account for anywhere from 60 to 80% of our capital expenditures in a deep geothermal process. We need cheap, quick, effective borehole drilling. But maybe we can achieve that, you know, in our granitic rocks, in our crystalline rocks, in the Canadian Shield and in other places in the world, through the percussive techniques that your group is doing research on. And that's really what we need. Probably we can recirculate the cooled fluids through the rock mass, so we don't have to worry about disposing of fluids. But remember that as we cool the rock, we're going to have shrinkage. That's going to open up more natural fractures, and we're going to get a process called short-circuiting, thermal short-circuiting. We've published a couple of papers on that here in this last year. You can access them if you wish. The primary author is Bruce G, G-E-E, Rob Gracie, and myself. And also generating microseismic activity, because if we're cooling a zone, we're going to be dropping the stresses in that zone. Those stresses will be transferred to the shoulders, and we're going to have very large stress gradients, which will, of course, trigger shearing of the natural fractures. And just to show you natural fractures, about 3 years ago, I had an opportunity to go down to Tasmania. I recommend it to each of you, and have a look at some natural fractures along the beach there with a friend of mine who's also a geotechnical person. Yep. Now down below, they don't quite look like that. But one thing that we do know is that we're going to get channeling or short-circuiting because of a process of shrinkage and focusing of the flow in certain regions. So that one fracture will become the primary pathway, and then that means we have more difficulty in mining heat from surrounding zones. Okay, now this is a very, very non-linear process, and that makes the mathematical modelers maybe happy, but also challenged. So when we write down the governing equations and start looking at the parameters, what some people call constants, we start to realize that in geothermal, nothing is constant. Our moduli are changing, at least at the scale of the rock mass. The moduli are changing. We're changing the permeabilities. We're changing the, well, I don't think we're changing beta so much. That's the coefficient of thermal expansion, but still, things are changing all the way. We're even changing porosity by the dilation of the apertures in natural rock masses. So everything is nonlinear, even the viscosity. If we're using water, at the beginning, we're going to have high temperatures. At the end, we're going to have much lower temperatures during our heat mining. The viscosity will change by a factor of 2 or 3. That will change our parasitic losses. Okay, so we need better predictive models because people that invest money into geothermal projects don't like uncertainty. For steam projects, we know how to de-risk them financially. But for enhanced geothermal systems, we're not there yet. We need better models to allow better predictions. We need improvements in hydraulic stimulation to link well bores that might be 400 or 500 meters apart. We need predictive models for induced seismicity. They don't exist yet. We have to marry rock mechanics with geophysics to come up with this type of predictive modeling. We have to have cheaper drilling. We have to learn how to use heat more efficiently. And it's not an easy road. You might ironically call it a rocky road ahead of us for EGS. So let's move on to compressed air, pumped hydro, and heat storage in the subsurface. This kind of evolves in part out of the natural gas storage industry, which is very mature. And I'll skip this slide to move on to why storage. Well, as we move more and more towards variable energy, the short-term energy variability that we see with wind and solar, we need to try to manage that. We also want to decarbonize, so we want more of that energy, and we have to store it. Storage might mean on a very short-term basis, hours, even minutes, but it also might mean storage for a longer-term basis, such as a week. But I remind you, you can't store heat or compressed air for a year. This is not natural gas. The energy density is very low. So you have to use your battery, if you wish to call it that, on a very regular basis to extract value from it. So wind, intermittent, but the costs are dropping. The Lazard report suggests the costs are now in the 2.5 to 5 cent per kilowatt hour range. Your Dogger Bank project is predicted to come in at around 4.5, 4.6 American cents per kilowatt hour. And then you're going to need to store it to try to smooth it out. Why? Well, wind looks like that grayish jerky line in the middle, but your grid demand is the red dotted line, and it's much smoother. So we have to somehow or other make those two fit, okay? I remind you that the variability is at all time scales virtually, from seconds to weeks. Sun, it's also intermittent. For example, and it's intermittent on a yearly basis. So here's what I downloaded for London in the UK, and that orangey color there, I'm a bit colorblind, I think it's orangey. That's the statistical variability at the 95% or 99% limits for each summer. Look at how variable the solar energy is in London from year to year. It's that orange line. How do you design an energy storage system to work well with a grid if you're using solar power? Well, maybe solar power isn't what the UK needs. Maybe the UK has to focus on wind power, and indeed you're doing that with your huge offshore wind farms that you are now building on the Dogger Bank and of course in Scotland and other places. So energy storage is to change the time of use, but also to smooth it, and to provide other ancillary grid surfaces, such as what we call load following capability, to provide inertia. Lithium-ion batteries don't provide inertia for the grid, whereas spinning equipment like a compressed air energy turbines, they do provide what we call inertia for the grid to stabilize the grid. Okay, safety and reduction of costs of energy provision. I do not believe that the Tesla's Megapack batteries are the final answer. I think that we're going to have to look much, much more at subsurface storage. Batteries have their problems. Pumped hydro, well, nobody wants to flood nice valleys anymore. So pumped hydro means maybe using old mine shafts. That's certainly possible, but there are severe limitations, especially in arid climates. Pumped hydro is simply, not possible. Now in Norway, of course, with the mountains right by the seacoast and with all kinds of freshwater rivers coming down, Norway can use pumped hydro very, very effectively. Down in Kent or around London, no, it's not it's not going to happen. In Saskatchewan, no, it's not going to happen. So in some cases, yes. Compressed air storage, it's great, and it's got a long history already, but it is lower efficiency in conversion. Whereas 95% conversion efficiency is possible for batteries, well, actually 98%, and pumped hydro is more than 85%, maybe 88, 90. Compressed air storage runs between 50 and 70, depending if you are scavenging the heat and reusing it to heat the air. Hydrogen, we're not ready for that yet. We need another 20, 30 years before we're going to have a significant amount of hydrogen in our energy economy. And I don't see any magic bullets out there. I do not believe that modular nuclear reactors are going to live up to the incredible hype and the incredible claims that their proponents are publishing these days. There are many problems that are not solved, including, let's see, what community will accept modular reactors in their backyard? The NIMBY issue is always going to be with us. And of course, danger. This is a battery fire on August the 21st in Geelong battery farm in Australia, which shut things down for quite a while. And there have been other lithium battery fires. So I don't like batteries personally, but then batteries sit on the surface. And as you know, I'm a subsurface person. So I favor anything that's at least 100 meters deep. The compressed air energy storage concept is fairly straightforward. You take power, excess grid power as well, for that matter. Compressed air, if you can, store the heat from the compression, because the heat is going to help you by heating the air going into turbines to keep the air from freezing and extracting the energy. Your storage medium can be, in this case, salt gallery, which is actually a void, a compressed air filled void at depth, or we can use a saline aquifer. So in this configuration, you see that we have horizontal wells, and they're pushing down the water-air interface in a quadruply closed anticlinal type or dome type reservoir of very high permeability. I have to have very good vertical permeability for this. And then when we want the air, we can get it out. But there's more losses in an aquifer storage because of the flow through the porous medium. Salt caverns, we know how to design them. We've been designing them and using them for natural gas storage for more than a generation. There are two operating compressed air large-scale grid projects in the world. One in Germany, in Hunddorf, has been operating for over 40 years, and the salt cavern is absolutely performing perfectly. And by the way, batteries last 7 or 8 years. Salt caverns, indefinite. The other grid scale facility is in McIntosh in Arkansas in the United States. Both of them happen to be associated with a nuclear power plant. The third project that is commercial now is a very small demonstration project, and it's the first one that's adiabatic, mostly adiabatic. In other words, they are storing the heat in oil and using the heat to heat the air going into the expanders. It's very modest delta P, only about 600, 700 kPa, but excellent performance so far at 1.75 megawatts output. And it's a demonstration project. Ontario has excellent conditions for scaling up to grid scale. So this is the actual physical cross-section of the cavern at depth, 410 meters deep. An old solutioning cavern, and that's not the best. You can see the shape is kind of wonky here. So this is the well bore. Up on the hill is the plant. On the right-hand side are the heat storage tanks for the oil, and the oil is heated up to 300 degrees Celsius by the air by the compression, and then of course during the output phase. All right, so that's Dogger Bank in the middle of the North Sea there. And it's underlain by the Zechstein Formation halite, which of course intersects in Newcastle, and you have potash mines up in that little corner of England. And that also means you have good salt for storage of the variable component of the wind power to smooth it out and help the whole process of integrating more wind power into the grid. We can do that, but you need the storage. And I mean large grid scale storage at the gigawatt scale. And the storage of 10 gigawatt hours, 20 gigawatt hours, that's the scale that you need in the United Kingdom to factor the Dogger Bank in effectively. I don't know how much storage is being planned, but trust me, more is better. However, we can use cased well bores for compressed air storage as well. So a cased well bore that is a kilometer deep, 30 centimeters diameter, is about 71, 72 cubic meters. And if you compress that up to 40 or 30 megapascals, you've got about 6 to 10 megawatt hours of energy storage in the cased well. And again, we can use that indefinitely. And it's not constrained by geology in this case. And if you want 2 of them or 10 of them or 20 of them, then you can build an array of wells. And this is not a compressed air well. These are, again, natural gas wells. And the project that we're working on in Australia, in its early days, we don't have the money yet, but we're planning on putting these wellheads actually under the ground. So it'll be very visually okay. I'm going to skip a few slides here. This is compression on the left, storage in the middle, expansion on the right. Okay. So that means that to meet this grid demand in between the base load and the red dotted line, with this kind of irregular energy, we can store the irregular component and use compressed air storage to match that grid demand with storage. So compressed air energy storage not only provides all those other services, it also smooths everything out, so you have very, very good grid characteristics with inertia. I just want to mention that a ground storage heat pump is great in Toronto, where you need cooling in the summer and heating in the winter. But in the northern climates, all you want is heating. So you cannot extract heat indefinitely from the subsurface. The same thing in a tropical or a very hot climate. You need cool, not heat. So you can't continue to cool down the subsurface by extracting cool from it indefinitely. You'll end up freezing everything up, and your efficiency will completely drop. So let's just skip that. We're working on multi-dimensional aspects of shallow plus deep heat repositories and storage. Pumped hydro, underground mines. This is a concept that is being looked at around the world. I don't think there is a large-scale active project yet. We know how to do it. We have an underground pump house, an upper reservoir, and the lower reservoir in the mine. And when we have excess energy, we pump water up to the upper reservoir. When we want the energy, we pass it through the water turbines in the pump house and generate energy. There is a project being studied in Ontario here, and they're talking 1,000 megawatts maximum power output. And it's on the highlands along the Niagara Escarpment. And they have agreed to put the powerhouse and everything underground. So there's a huge amount of geomechanics and applied geology here that we're going to have to go through. I'm working on the stresses, actually. All right, so just to summarize, in subsurface storage issues, we need to understand the surface impacts, underground stability, thermal issues, again, microseismic concerns in some domains, the integration of these systems with the grid, and so on. But this is a really, really rich area to work in for geoscientists and others. I've summarized 3 ideas here, and I'll just briefly summarize them again. As we are moving to a carbon light world, we have to find better ways to generate, store, and use energy. And we can't solve one problem, say generation, without solving the others, the storage problem to smooth out the deliverability and the transmission and use of that energy. And of course, you're always thinking electrical power, but no, it's not just electrical power. It could be heat. It could be cold. Remember that Mumbai and Chennai would like to have the subsurface used as a nice place to store cold when you can, and use that cold in the heat of the day with ground source heat pumps, of course. Because the Earth is hot at depth, hopefully we can exploit this for heat and power. Another little point I just want to leave with you is that in a very cold climate, heat engines at the surface, the organic Rankine cycle, are actually substantially more efficient, because you're moving to lower temperatures on the Rankine cycle, or kelvins. You're moving to down the Kelvin scale towards the left, and it gets more efficient. We want to use a subsurface not only for these things that I've mentioned, but also for disposal of wastes, liquid and solid wastes. We store huge amounts of, or we dispose of huge amounts of waste materials in sedimentary basins, like produced water and acid gases. Sequestration of carbon, we're all interested in that. And maybe even, looking at the underground more and more as a low heat loss habitat and storage, etc. So I'd like to thank John Paul for inviting me to give this talk on the use of the subsurface. And of course, naturally, I wouldn't be here without the work and the effort of the network that supports me and that supports us in this area. Thank you, Mark.
Well, I'd like to thank Maurice for a really fascinating talk. Good to see that the prospects for use of the subsurface are strong. Oh, there's a horrible echo. Not sure you're getting that as well. So if you have any questions for Maurice, please put them in the chat. We have got some to kick off with. If you've got any more coming up, please go ahead. So I'll relay those on to Maurice. So you talked at the beginning, Maurice, about using natural gas as a bridging energy source until we can get hydrogen established. There was a question about distributing hydrogen, the question around whether we can just reuse old methane infrastructure for that, or whether we need to replace that infrastructure in any case, given the difference in molecular size between hydrogen and methane.
Well, that's an excellent question that is worthy of a lot of research, because what we want to do is, if we can, is to repurpose infrastructure. But suppose that we are building out infrastructure right now, let's say working in India, okay? In India, which is burning a lot of coal. So let's say we do get involved in that. Well, can we build infrastructure that is hydrogen friendly as well as methane friendly? Now, remember that we may not use hydrogen purely as an elemental substance. We may use hydrogen as a 50-50 mixture with methane, or a 20-80 mixture with methane. Gradually, as our hydrogen supply increases over the decades to come, then we may want to reduce the amount of methane. So the idea is build new infrastructure, new natural gas infrastructure with view to hydrogen in the future. Number two, see if we can retrofit, improve existing infrastructure by various means to cope with the very small molecular size and the very high diffusivity of hydrogen. For example, we do store methane in porous media in the subsurface. It's unlikely that we'll be able to store hydrogen in those same reservoirs, because already the kind of reservoirs that we use to store methane have leakage rates of about 1% a year, typically. Well, if you substitute hydrogen, 100% hydrogen, you're going to be leaking at about 30% a year. And we can't have that. So maybe we're going to be restricted to those well bores that I showed, high pressure well bores. I can store in that well bore at 40 megapascal, I can store 2,600 kilograms of hydrogen. So that's another way of storing it. Or salt caverns. Most of us believe that salt caverns, properly dissolved with reasonable shape and good quality cementation on the well bores, that hydrogen can be stored securely in pure hydrogen storage in salt caverns of limited volume, maybe 50,000 cubic meters instead of huge salt caverns. So I think that these are solvable issues.
Great, thanks very much, Maurice. Okay, the next question was around the biosolids that you talked about, and there's a question around the injectivity of the biosolids. You showed an image; it looked like a pretty nasty slurry. We find even injecting water into subsurface formations can have unexpected consequences in terms of permeability reduction and so forth. So the question really is, can we be confident that you'd maintain injectivity, putting that very complex fluid into the subsurface?
Good question. And I want to point out that no injection of a slurry is possible without hydraulic parting. I use the term hydraulic parting because we're not fracturing the rock. These are ductile rocks. They're sandstones of 25% porosity with minimum cementation. So fracturing is the wrong term. I refer to it as hydraulic parting. So we're doing hydraulic parting of the rock. We're creating our own volume. Then the slurry enters into that volume, the slurry itself creates the volume, and then it is very aggressively dewatered by the high stresses and the high pressure gradients in the ground. But yes, with time, we're going to be blocking the pore space more and more and farther out from the injection well, which is why I had one bullet in my presentation there is, what is the capacity of a single well? Well, that depends on geology. That depends upon geology and geomechanics. But it seems entirely reasonable to think of perhaps 100,000, 50,000 cubic meters of solid waste, dry equivalent solid waste. Now, to put that into an economic perspective, 1 cubic meter, 1 ton of dry solid waste, which is less than a cubic meter, in California, in Los Angeles, costs $120 US in order to treat with current technology. So if you say we can put 100,000 of that into one well, let's see, that's $10 million. And a well bore at 600 meters deep doesn't cost 10 million, it costs 1 million. So you can see there's a lot of economic and commercial leeway here to actually treat biosolids more cheaply than we currently do, and yet at the same time generate methane and sequester carbon. I mean, what's not to like about that? Now, we're not going to do this, underneath Waterloo Station in the London clay. We're going to be doing this in high porosity, high permeability sandstones, and maybe even offshore, like in the Thames estuary to the north there, where we don't have commercial shipping coming through. That would be a reasonable place to do this. But it all depends upon the geoscience modeling and understanding the geomechanics and monitoring, of course. Yeah.
The monitoring, that's perfect, Maurice, because that leads me right into the next question, which was, how could those stress changes and other subsurface changes be monitored during biosolids injection?
2 ways dominantly. One is a microseismic array, which gives you information about the slipping that happens, as a result of the large strains that we're doing, whether they're thermoelastic strains or whether they are physical strains induced by the volumetric injection of the biosolids, for example. But the other technique, which has been perfected over the years, is the deformation measurements. So we now use tilt meters that can measure very, very easily the transit of the moon overhead. It actually gives you quite a large signal. So we're measuring into the nanoradian range. And also satellite technology now for large-scale land-based systems gives us an ability to track the surface uplift at the scale of sub-centimeters now, into the several millimeter scale reliably, so that we can use those deformations and do mathematical inversion. I'll show you how to do them to actually track the volumetric changes in the deep subsurface. And that gives us things that we can do, and then modify our process accordingly if we need to modify it. The microseismic issue is a really important one. Nobody yet knows how to predict the microseismics, the microseismic level, what magnitude, what recurrence rate. Remember the Basel experiment, EGS. Nobody expected that. I mean, nobody. So here we are, and the geophysicists can't do it alone, and the geomechanics people can't do it alone. We got to work together and combine rock mechanics, stress changes, thermoelasticity, and all these kind of things, along with the signal analysis and signal processing and the the geophysics models. We have to create a new integration of these two areas very, very intimately in order to crack that nut. And trust me, our wonderful civil servants are not going to give us permits unless we can assure them that we have a better predictive capacity for these microseismic emissions.
I think that's a great place to wrap up today. We're just about out of time, but yeah, pointing out the important, we are going to remain important as geoscientists, geophysicists, and geoengineers for many years into the future. So I'd like to thank Maurice again for a really fascinating talk, an encouraging talk for us as geoscientists, and to wish him an enjoyable breakfast now. He's going to be chatting to JP Latham at 2. JP, I don't know if other people would like to talk to Maurice a bit later in his morning and our afternoon. Perhaps let JP know, and he could always pass you over to Maurice once he's had a chat with him about geothermal drilling. But thanks again, Maurice. Really enjoyed that.
Yeah, thank you. And if anyone wants to drop me an email, I might be able to I generally try to answer my emails as long as there's not a flood of them. But so drop me a line, and thank you.
Yeah, thanks, Maurice. Take care. Bye-bye.
Take care. Bye now.